Hello.
How are you doing today?
Good. What about you?
Good. So what do we got going today?
Well, today I have a quiz tomorrow, so I'm just kind of going over everything that's going to be on.
Okay. Stuff you can verbalize?
Yep. I have a sheet with questions right here in front of me, so I guess I'll just read them out and we'll do it together.
Okay. All right.
So the first one is 5 log, parentheses, x minus 2 equals what?
I'm sorry. 5 times x minus 2?
5 log, x minus 2 equals what?
Like that?
Sorry. 5 times log base 10. Sorry, my bad.
Oh, that's okay. I just wasn't sure whether I was not using terminology correctly.
Sorry.
So it's 5 common log base 10
Mm-hmm.
of x minus 2 equals 5, right?
Yep.
Okay. So what's our first step going to be?
Right here, wouldn't you just kind of take the 5 log and put it on the other side, so it'd be 5 squared equals, or 5 to the root of 5 to the 5th power equals x minus 2. Sorry.
Well, that's not really what we want to do as the first step. One thing we could do is this, but that doesn't really help solve the problem. It makes it more complicated. In other words, we could use the rules for logs to do that. But we can definitely divide both sides of this equation by 5 so that we get log of x minus 2 equals 1. Now we have the log isolated, so I can turn it into exponential expression and then solve it. So what would the exponential expression of this be?
Wouldn't it be log base 10 times 1 equals x minus 2?
Well, the way I usually convert my log expressions to exponential expressions, just the way I remember it is it's the number on the far left raised to the power of the number on the far right, and it equals the argument. So I end up with 10 to the 1 equals x minus 2. Now x equals 12. Okay. What do you got next?
It's just kind of a different kind of logarithmic version. It's 4 to the x minus 1 equals 10.
4 to the x minus 1
Equals 10.
Equal 10. Okay. I'm having a little bit hard time understanding what you're saying.
Sorry.
Okay. This is not an algebraic expression. I can't solve it algebraically. I have to invoke logs to solve this. Hold on. Bye, come here. Bye. Stop barking. All right. Since neither of these numbers have a common exponential base, if they did, I could solve it without using logs. In other words, let me just give you an example. If I had 9 to the x equal 27 to the x minus 1, both of these numbers have a common exponential base of 3. So I can let the 9 be 3 squared to the x power. I can let the 27 be 3 cubed to the x minus 1 power. I can then use my rules of exponents, make that, and make this. Now that I have 3 to an exponent equals 3 to a different exponent, I can equate the exponents and solve. X equals 3. So you'll see these kind of problems all over the SAT and the ACT. They don't require logarithms to solve because they have common exponential bases.
Yeah.
However, in this case, there is no common exponential base between 4 and 10. So we really have only one way of solving this, and that's by taking the logarithms of it.
Mm-hmm.
If I take the log of both sides, and I can use natural logs, I can use log base 10. Once you get up into math beyond what you're in now, natural log is going to be what everybody uses. Calculus is a natural log environment. It's not common log. So I typically just automatically, when I'm going to take the log of both sides, I take the natural log of both sides. Now, the reason I do that is because once I've got it in natural log format, I can take this variable that's in my exponent and I can bring it down in front. So that it becomes x minus 1 times the natural log of 4 equals the natural log of 10. Divide both sides by natural log of 4. In other words, that's just a number.
Mm-hmm.
Add 1. That's what x is equal to. You can certainly get those numbers off of a calculator. Okay?
All right. Well, I guess the next one, it's log base 2 times x minus 2 plus log base 2 equals x plus 3.
Plus the log base 2 of what?
Plus log base 2 of x equals 3.
Equals 3?
Mm-hmm.
Okay. In this problem, what am I going to do as my first step?
Aren't you going to want to compress into logarithm
Okay,
things?
good. So what's the resultant of that compression?
It'd be x minus 2 times x equals 3.
I'll go ahead and multiply them together. Now, once you have it in logarithmic format, the secret to solving it is to put it into exponential format. What's the exponential expression of this?
So it'd be x squared minus 2x equals 2 to the third power. So it'd be x squared minus 2x equals 3.
And now, how do I solve that?
You subtract 8, so it's x squared minus 2x minus 8 equals 0.
And then, the standard quadratic that you can factor.
I'm really at this.
Okay, let's go over factoring. That's the first step. A lot of people have trouble with factoring, but if you just remember the 4 initial steps, it takes care of 90% of your factoring problems. Step 1 is to find out x and x multiply together to give you x squared. Step 2 is you examine the sign on the constant, this negative sign in front of the 8. That means the signs here have to be opposite. It's the only way you can produce a negative number is if you're multiplying a positive times a negative.
Mm-hmm.
Now, the third step is find factors of 8. That is, 2 numbers that multiply together to give you 8. That subtract, because of that minus sign, to the number 2. Well, that's 4 and 2.
Yeah.
You put the bigger of those factors with the sign that is on the middle term. So my 4 goes here, my 2 goes there. If I want to check to see whether I've done it correctly, I'm going to just check the inside and the outside. I know the x squared is right, and I know the minus 8 is right. The one I want to check is that minus 2x. Well, 2 times x is plus 2x. Minus 4 times x is minus 4x. Add those together, you get you get minus 2x. So we did it right.
Yeah.
So, what's x equal?
X is equal to 4 or negative 2, but then
Which one doesn't work?
Negative 2 is extraneous because negative 2 minus 2 is negative, and you can't have a log.
Negative 2 violates the domain of log functions, precisely.
Yep.
Now, let's for the moment take away that minus 2 right there. You with me?
Mm-hmm.
In other words, we had the log of x plus the log of x, and the first thing we did was combine it into this. And now we get a negative solution. Let's say our solution, again, I don't know what it is. We'll say minus 3 and plus 4. I'm just making this up. Okay? Notice that if I take my negative number and plug it in for here, it does not violate a domain. But if I plug it back into the original, it violates the domain. And what that means is that these two statements are not equivalent. We kind of say they are equivalent because we talk about the log rules and everything. But in terms of domain violation, you always have to go back to the starting equation. Always. Because otherwise, this problem creeps up, where once you square it, now even a negative number squared is going to turn positive. So you wouldn't violate the domain in this step, but you'd still violate it in that step, which means you'd violate it and there would be no solution here. Okay?
Yeah.
All right. That's a difficult thing to understand because we talk about those two first equations being equivalent, and they are not equivalent for regards of domain.
All right. And then next, do you know explicit and recursive rules?
I'm sorry, what?
Do you know explicit and recursive rules?
Yes.
All right. Well, next is just write an explicit and recursive rule for the following sequences, which is 5, 15, 45, and 135.
5, 15, 45, and 135. What kind of series is that? Is that arithmetic or geometric?
Isn't that arithmetic?
Arithmetic have a common difference between each term. Geometric has a common ratio between each term. Well, the common difference, that's 10, that's 30, so it's not arithmetic, but it is geometric, because if you take any term and divide it by the previous term, you get 3. So it's a geometric series with a common ratio equal to 3. Now, for a geometric series, the explicit term is the first term times the common ratio to the n minus 1. Now, let's talk about that. How does that work? Well, a sub 1 is the first term, 5. A sub n is the nth term. Well, let's say I wanted to know what the third term of this series was. So I want a sub 3. Well, I'm going to get it by starting with 5. The common ratio is 3, and I'm going to take 3 to the 3 minus 1, 2 power. So a sub 3 is equal to 45. That's my third term. So by this definition right there, you can figure out whatever term you want. You could figure out the 149th term if you wanted. Now, that's the general. Since we know this, then really my explicit formula is that right there. This is the general explicit formula for a geometric sequence. This is the specific explicit formula for this geometric sequence. Let's talk about the recursive formula.
I'm not too familiar with that one.
I'm sorry, what?
I'm not familiar with that one. I don't really know.
Okay. Recursive merely means it's expressed not as a function of the first term and other stuff, like this one is, but it's expressed as a function of the previous term. Well, if I'm going to make it an expression of the previous term, well, what is it? It's 3 times the previous term, right? In other words, the fourth term, a sub 4, would be equal to a sub 3 times 3. Well, that's 45 times 3, 135. So this is the general formula for an explicit. The general formula would have an R right there. In other words, the recursive formula is the nth term is equal to the nth minus 1 term times the common ratio. And specifically for R's, a to the n is equal to a to the n minus 1 times 3, because we know the common ratio is 3.
All right. Yeah, I understand that. All right.
Now, let's talk about the arithmetic sequence, as long as we're talking about sequences.
Okay.
If I write a sequence like this, each of these is separated by a common difference. D equals 2, the first term equals 2. The general formula for arithmetic sequences, the general explicit nth term formula, is the first term plus the common difference times n minus 1. So the fifth term, a sub 5, according to our first term, is 2. Common difference is 2. N is 5, so I'm going to multiply that by 4, and I get 10 as the fifth term. So the specific explicit nth term is for this sequence is 2 plus 2 times n minus 1. And I suppose you could simplify this if you so wanted to. In other words, that's equal to 2 plus 2n minus 2, so this is actually 2n. In other words, I could simplify this to say a to the n equals 2n, which it does for this particular sequence. Fifth term's equal to 10. The sixth term's equal to 2 times 6, 12. Now let's talk about the, not the explicit, but the recursive way to define an arithmetic sequence. Once again, recursive means defining it not as a function of the first term, but as a function of the previous term. So the recursive almost always is going to start out like that, regardless of whether you're talking arithmetic or geometric sequence. Well, what is it? In this case, it's the previous term plus the difference. It's as straightforward as that. So this is recursive. And so now we have a sub n equals a sub n minus 1 times 2. So there's the specific one for our sequence.
Yeah.
So both your arithmetic and your geometric sequences have two different ways to refer to them. There's the explicit way and there's the recursive way. The more common is the explicit, that right there, because you usually know the first term in a sequence.
All right. Next one, I guess we should just stay on sequences.
Yeah, sequences are a pretty good topic. I mean, there's a lot to sequences.
For this next one, it's just, so it says find the series, or find the term, and it's 1 plus 4 plus 16 plus 64.
1
plus 4. Yeah, sorry. 16 and 64.
Kind
And
of
it says find the 10th term.
Okay. What kind of sequence is that? Arithmetic or geometric?
That's geometric.
What's the common ratio?
4.
So the general is, once again, you remember what it is?
I should remember.
The explicit always starts with the first term. The recursive always starts with the previous term. In other words, a sub n minus 1. Well, you're asking about the 10th term. Well, we don't know what the 9th term is. So we want to work with the explicit definition. So it's a sub 1 plus the common ratio times n minus 1. And this n minus 1, hold on, common ratio to the n minus 1 power, like that. Okay, so we want the 10th term. So the first term is 1 plus the common ratio of 4 raised to the 9th power.
All right.
If you have a calculator, you can come up with that number.
Yeah. 4 to the 9th is 262,144.
262,144 plus 1, 145. No.
Yep.
No. Oh, yes. No. Hold on a second.
All right.
No, one moment. I've made a mistake here. I'm trying to figure out what I did. The reason I know I made a mistake is because all these terms have to be divisible by 4. Right?
Yeah. Yes, I do.
It's a sub 1 times r to the n minus 1. In other words, the third term would be 1 times 4 squared, or 16. So the answer to the 10th term is merely 1, the first term, times 4 to the 9th. 4 to the 9th was this number, so this is the answer.
All right. So it's multiplication, not addition. That's why.
Yeah, it's been a while since I have looked at arithmetic sequences, I can easily make that kind of a mistake. And you also have the sum of both arithmetic and geometric sequences. I don't know if you've gotten into that yet.
No.
Okay, well, let's not go over it then. We've only got 4 minutes. Do you want to do one more problem?
Yeah, sure.
Okay.
Wait, sorry, what was the thing that you said previously that you asked if I've gotten into?
The next thing that you would learn about arithmetic and geometric sequences would be the sum. In other words, it'll give you a series and it'll say, what's the sum of this series from 1 to 100? In other words, if you wanted to know what the sum of the numbers 1 through 100 was, there's a formula for that.
No, we haven't gotten over that.
Okay.
I guess the final one I probably want to do is just finding what the term is when they give you a number. So with the same one, 1 plus 1, 4, 16, 64. And then they give us one of the SN equals 21,845.
How much?
21,845.
Okay. We do need to know what sum is. In other words, they're saying how many terms are in this, right?
Yeah.
Okay. So we need the formula for sum of a geometric series. And the formula for the sum of a geometric series is a sub 1 times 1 minus r to the nth all over 1 minus r.
All right.
And let me see if that, no, that's fine.
I thought, I'm pretty sure that 1 minus r, you divide only 1 minus r to the nth divided by 1 minus r. I think that's in parentheses.
Let's see. Well, let's solve. This is the formula I have in my book, and we can put a lot of blanks in here. So we got 21,845 for the sum. They've told us that. So that's going to equal, a sub 1 is 1. So we have 1 minus, the common ratio is 4 to the n, and that n goes inside the parentheses, not out.
Mm-hmm.
All over 1 minus 4. So now, if we try to solve this, we've got 1 minus 4 to the n all over minus 3. Well, if I multiply that number by minus 3, what do you get?
I got negative 65,535.
500 and what?
And 35.
Oops.
Mm-hmm.
Subtract 1 from both sides. Divide both sides by minus 1 because this n does not act on that negative sign, just the 4.
Mm-hmm.
So I can do that. And now I have 4 to what power equals that? Well, how do I solve that equation?
Wouldn't it be log?
Yeah, take the natural log of both sides. Now you can take that n, stick it there, And you've got n is the natural log of that number divided by the natural log of 4, and that's how many terms there are going to be in that sequence.
All right.
Whatever that is, you'd have to look that up on your calculator. But that's what n is. It's probably a pretty good size number, I would think. It would be like 50 maybe, 40, something like that. But anyway, I have another 4:30 appointment, Garrett, so I am going to have to rush.
All right. Sorry to hold you.
Hope this has been helpful. I will talk to you next time.
All right. Sweet. Thank you.
Bye-bye.